Hello, I'm Clara and I will present joint work with Schrijvers, Oliveira and Karachalias on subsuming resolution through subtyping with intersection types and Modus Ponens. Resolution is a programming language feature that involves an implicit context which contains expressions and their types. This context can be inspected and its values can be combined as the system tries to infer an implicit expression of a desired type. To see how it works, on the right is a simple Scala example that uses resolution, and the situation is depicted on the left. The first three lines define two values and the implicit keyword inserts them to the implicit context. The first value is the true boolean assigned to variable t, and the second is the bool_to_int function which produces an integer given an implicit boolean. The last line asks for an implicitly inferred integer. So resolution looks up the implicit context for an expression with a matching type, and it finds bool_to_int, which requires an implicit argument in order to produce that integer. So resolution continues recursively for a boolean this time, and the matching expression is a variable t, which is then passed to the previously found bool_to_int function, at which point resolution succeeds and returns bool_to_int applied on t. Subtyping is omnipresent in object-oriented languages. Essentially, it is an ordering over types or over classes in the object-oriented setting. In the subtyping judgment that we see here, T1 is a subtype of T2, and we can think of this to mean that expressions of type T1 can also be considered to have the compatible type T2. In coercive subtyping, furthermore, the judgment produces a coercion which captures how to convert an expression of type T1 into an expression of type T2 through a coercion application. There are languages that support only one of the two features. For example, Haskell has type class resolution but not subtyping, and Java supports class inheritance but doesn't do the kind of resolution shown here. And although resolution and subtyping have been studied separately in the literature, there are languages like Scala that support both features in a way that they interact. Here is a simple example of the interaction. The first two lines in this code define classes A and B and establish that B is a subclass of A. Coercion C here acts as a function that expects an object of class B, and it drops from it all the additional information that class B contains and returns an object of class A. The next line defines object B, an object of class B, and inserts it in the implicit context. In the last line, we ask for an implicitly inferred object of class A. So resolution alone here would fail because the implicit context only contains a class B object while we're asking for a class A object. However, if the information in the implicit context is combined with subtyping, then the mechanism succeeds because it can apply the coercion to the implicit object B and return an object of the desired class. So in this talk, resolution and subtyping keep their interaction alive and actually they unite in the church of intersection types. Intersection types have been used by the research community in various ways. Pottinger and independently Kopo used them first to characterize the strongly normalizable terms of the lambda calculus, but intersection types have been used to enable several language features as well, such as refinement types, multiple inheritance, and other kinds of polymorphism. In our work, we use an interpretation of intersection types proposed by Dunfield, in which we can have expressions of types like int and char. These are expressions that are both integers and characters. To construct them, we use the merge operator, which takes two expressions of possibly different types and merges them into an expression of the appropriate intersection type. Internally, intersections are translated into products and merges into tuples. And since we can have expressions that can be both of one type and of another, we can choose how to use them by appending a type annotation to them. So for example, here we want to use this merge as an integer. The type annotation triggers subtyping, and in subtyping with intersection types, intersections are subtypes of their components, and the produced coercion is the appropriate projection. Here, the projection on the first component. Internally, this coercion is applied to the tuple that corresponds to the initial merge, and finally this application reduces to the integer we have been asking for in the first place through the type annotation. Here I have used a very simple example to illustrate how the type system works, but we can do more interesting things like to merge two functions, which makes it more obvious that this setting enables finitary function overloading. The basic idea that connects resolution and subtyping is that we can interpret the left-hand side of the subtyping judgment as the type of the implicit context, and the right-hand side as the wanted type. Then the produced coercion witnesses how to extract a value of the desired type from an implicit context of the given type. A notable difference is that in resolution, the implicit context contains the implementations, while subtyping considers only the type of the implicit context. But this is not an issue because implementations can be provided separately, usually as merges, and then the wanted type can be specified through a type annotation. The fact that we treat expressions as potential implicit contexts allows us to have multiple first-class implicit contexts that can live under the same scope. But apart from the practical benefits that we gain, expressing resolution as subtyping is an opportunity for us to study the two features together and how they interact. There is still an ingredient missing, which is that if resolution can infer an integer from an implicit context that contains a boolean and a bool to int function, then subtyping should be able to do the same. For that reason, we extend the subtyping relation with a rule that resembles Modus Ponens from logic and simulates the kind of inference happening in resolution. This rule expresses that if a type is a subtype of a function type, and it is also a subtype of the function's domain type, then it is also a subtype of the function's codomain type. So, for example, if we look at the left-hand side of this subtyping judgment as the type of an implicit context, then by projecting on the first component, we get a bool to int function. By projecting on the second component, we get a boolean, and then by applying the extracted bool to int function to the extracted boolean, we get the integer just as resolution did on the left. To see an example that approaches a more realistic situation, suppose we want to process temperature measures taken from an experiment where the data is written in a comma-separated string. Sometimes the sensor may fail to read the temperature, in which case, instead of writing an integer, it writes a string, possibly indicating the reason of the error. It would be sensible to try to parse the string as a list of either string int values. Our language comes with some predefined functions for reading values from a string, but the problem is that to use them, we would have to provide our data in a different format in order to successfully parse it. To solve this problem, we can define our own custom functions for reading values from a string and use them in a custom environment. First, we create the readA type alias, which stands for the function type string to a. Then we can define our custom functions. ReadEitherSI is a function from string to either string int, which is parametric over readString and readInt functions. And readListSI expects a function of type readEitherStringInt and returns a function from string to list of either string int. So once we have defined our custom functions, we can merge them with the predefined functions for reading integers and strings. The type of this merge is shown right above, for which we create the sensor type alias. This big merge, which we actually assigned to the env variable, will serve as our custom environment. To do that, we create the readSensor function, which expects an argument of type sensor and annotates it with the appropriate type, read of list either string int. It is this function that will do the job of resolution, but through subtyping. So once we call readSensor with our custom environment env, it will pass readString and readInt to readEitherSI, and it will apply readListSI to the result. We are now ready to define our function custom read, which takes a string and parses it as a list of either string int functions. In fact, we can do more. For example, we can define another function, readTry, which takes two sensor environments and a string and tries to parse the string with both environments, possibly indicating whether one of the two environments fails. This is all very nice, but there are issues at stake. A desired property for languages with non-deterministic semantics is coherence, which practically means that if we use two compilers of a language to compile the same piece of code, then the resulting programs, although not necessarily identical, they should be indistinguishable to the external observer. Consider, for example, this expression. There are two ways to extract an integer from this merge. One by projecting on the first component and another by projecting on the second. Importantly, the two results are not equivalent to the external observer, so coherence breaks. To prevent this kind of ambiguity, we allow merges only between expressions of disjoint types. This idea has been taken from previous work by Oliveira and has been adapted to the needs of our work. So with this restriction, expressions like this one of the previous slide are not allowed. Similarly, merging the value 2 with true and bool to int is also not allowed, because if later we annotate this merge with int, we will have again two ways to extract an integer. One by projecting on the first component, and another by using Modus Ponens on the second and the third component, which would yield a different result. However, we can have this situation. We can have the literal one annotated with the type int and int, although no type is disjoint with itself. And this is because the disjointness restriction is imposed only on merges and not on type annotations. We can also merge true with bool to int, whose types are disjoint, and annotate this merge with int and bool to int, which is not a disjoint type. Internally, this would produce a tuple whose first component would be the result of a Modus Ponens application between true and bool to int, and the second component would just reflect the bool to int function of the initial merge. Now, since this intersection type, int and bool to int, is disjoint with bool, we could merge this whole expression with false, a new boolean, say false. False here doesn't conflict with true, because true has been lost in the internal representation of the expression through the type annotation. However, bool to int is still there, and it could be used via Modus Ponens and false to produce a new integer, thus again breaking coherence. So this example shows that by extending the subtyping relation with the Modus Ponens rules, there are cases that can slip away from this disjointness check. For that reason, we employ a stricter disjointness restriction, which rejects all of these ambiguous cases. And coherence is recovered. Actually, we have arrived very close to proving it, but didn't actually get there because of the overlaps that we allow through type annotations, which are hard to deal with in the proof. Our paper includes a more extensive discussion on the Modus Ponens subtyping rule, our disjointness restriction, and on our conditional coherence proof. It also presents a subtyping algorithm that uses two mutually recursive subjudgments. We prove that the algorithm is sound and complete with respect to its declarative counterpart, and is terminating when employed with a loop detection mechanism. The completeness and termination results were particularly challenging. You can find all the details of our calculus and algorithm meta-theory in the artifact that accompanies the paper, which also contains a prototype implementation of our calculus in Haskell. Thank you for watching.